Well, hello pre-calc students. I'm going to help you through the end of lesson 2 on orbits and eccentricity. So a couple like applications of ellipses kind of problems. So taking a look, this will be the last page of our notes that we're going to get to. Talk about Kepler's first law of planetary motion. It says that the path of a planet's orbit is an ellipse with the sun at one of the foci. So in the diagram here, we've got some object that's orbiting around the sun. Center would be here, but the sun is at one of the two foci. So we got a focus here, focus somewhere over here. Asteroids, comets, other bodies that orbit the sun, they follow elliptical paths, blah, blah, blah. Okay. The closest point to the sun in such an orbit is called the perihelion. Kind of highlight that right here. So as it comes by, this distance right here, or this point right here, would be called perihelion. So para meaning like approaching, and helion from Helios, the sun. Got some Greek and Latin connections there. And words given there. The farthest point, when it's at its furthest point away from the sun, is going to be way over here. And that we call aphelion. Ab meaning away, and the helion again meaning the sun. So like the furthest away from the sun would be the aphelion. I don't know if I'm pronouncing that right, but it'll be okay. The shape then of an ellipse is related to its eccentricity. So that's, comparing how close to a circle is it, like how flat is it, how stretched out is it. What you're doing when you're finding the eccentricity is you're comparing E, the eccentricity, is equal to C over A. So it's the ratio of C to A, where C, if you remember, is always going to be the distance from the center to a focus. So that'd be C, in this case the distance from the center to the sun. And A is always going to be that distance from the center out to a vertex, half of the major axis. So if we compare those two things, we take C over A, it's going to be the ratio of C to A. So the closer that C is to A, the bigger that C is. If C were to be, really wide out here and really close to A, when you were to divide those two, you get a number that's closer and closer to 1. The closer you are to 1, the flatter this thing is, and the closer it's going to be to like being essentially just a straight line and not an actual ellipse. The smaller that C might happen to be, use blue instead here. If it's way in here, well, then it's going to be a little bit more of an oval type shape, a little bit closer to a circle. And in that case, C over A, sorry, you can't see that, would be a little bit smaller, close to 0. A circle, for instance, would have an eccentricity of 0 because the foci is at the same spot as the center. I'll show you what I mean. Got here on Desmos an example where I've got two different ellipses graphed. One that's going to be stretched more horizontally and one that's stretched more vertically. And I got sliders set up for A and B. A is going to be the major axis length. So right now I have a major axis length, or half of the major axis is 3, semi-major axis. So 3 to the right, 3 to the left. My minor axis is also set to 3 at the moment. So 3 up, 3 down, thus we have a circle. Now as I change A, what happens is my two different ellipses stretch out. Okay, I'm going to left B the same, it's just A is switching and changing from 3 and stretch itself out. This little red dot right here, excuse me, represents the focus. So I have set up an equation where C is equal to the square root of A squared minus B squared. So it's using the Pythagorean relation with an ellipse and plotting the point C comma 0 and negative C comma 0. Or in blue, 0C and 0 negative C for the up and down ellipse. In any case, as I stretch my ellipse, so right now it's basically a circle, my foci, if you notice, the dots are spreading themselves out. And as they spread themselves out, they're getting closer and closer to those vertices. Okay, so the value of C is getting close, which again would be this distance from center out to the focus, is getting pretty close to the distance from the center to the vertex. So, or from, look at the vertical one, distance from center to focus is getting close to the distance from center to vertex. The closer those two things are, the flatter our ellipse is going to be. So that would be the eccentricity of an ellipse is describing that shape. I'm going to use it. Problem something like this: the orbit of Halley's Comet, 36.18 AU. That's astronomical units. which is pretty close to the distance from the Earth to the Sun. So you can picture that. Halley's Comet is orbiting, its orbit, it's elliptical, it's a comet, and it's 36.18 astronomical units long and 9.12 astronomical units wide. I would consider this to be the length of the major axis, and this to be the length of the minor axis. Okay, so keeping that in mind, I'm supposed to find its eccentricity. Well, to do that, I need a couple things. I need A and I need C, right? Because E is equal to C over A. C is the distance from center to focus. A is distance from center to vertex. A is half of the major axis, the semi-major axis. So A, we'll make a little note of what these are. A is equal to half of 36.18, which is going to be 18.09. B will be half of the minor axis, which will be half of 9.12. That is, I'm going to write down 4.56. And then I'd have to do a little work to find C using my Pythagorean relation, So I'd be taking the A squared, this big guy, minus B squared, taking the square root. And I did that already and got 17.51. So that's the value of C. That's the distance to the focus. So setting up my equation then, I take C, 17.51 divided by A, which is 18.09. And I end up with about, and this is a rounded answer, 0.9688. Let me write that down. 0.9688. So that'd be my eccentricity, which is pretty close to 1. That means this is actually a pretty flat elliptical shape that Halley's Comet takes on for its orbit. One more problem involving applications of an ellipse. Lithotripter. So a lithotripter, is a machine that's used to help break up kidney stones. So if you ever had a kidney stone or know somebody who has, super painful, and one of the treatments is to use this lithotripter. So it generates some UHF shock waves and bounces them off this chamber, and as it bounces off the chamber, everything, all these waves get sent to the patient's kidney stone. So you're focusing all this energy on that one spot, and again, you're able to do that because of the way that ellipses work, and that the sum of these distances that I'm drawing are all the same. So I know that I'm going to go from focus to focus and hit that spot. So the question we're asked is, if this thing has a major axis of 12 and a minor axis of 5, how far from the center are the foci? Well, A is half the major axis, which is 6. B is half the minor axis, so that's going to be 2.5. And I know that if I need the distance to the foci, that's C. And A squared is equal to B squared minus C squared. It's plus C squared. So I'll subtract those two things. 36 minus 6.25. Let's skip ahead a little bit here. Is 29.75. And that's what's equal to C squared. So then you take the square root of that, and as a decimal, the distance that you would travel from the center to the foci and where you would place your patient would be about 5.454 feet. So there's a couple of applications of ellipses and a little look at the idea of eccentricity. Hope that helps.